So we're picking it back up about halfway through section 1.2. Once again, this section is somewhat long. We're going to start with page 14. And in this case, we're still talking about intercepts. Okay, and now instead of a graph, they're telling us to use our calculator to estimate the x and y intercepts of this particular function q. So I'll just simply bring up my calculator. And I'll start typing in the expression for q. I've got an x to the fourth power. Remember, to get out of your exponent, you simply just want to hit the arrow right key. Okay, now I have a minus 5x to the third power. I have another minus 5x squared. I have a plus 23x, and then a plus, I got two pluses, 10. Enter. Okay, and just where our graph was previously, we can see parts of it. Alright, but I want to see my x-axis, and I want to see where this curve crosses the y-axis, so I can't use this particular graph. So I go to zoom, and I am going to zoom out, and I'm gonna go up and center my graph close to the top of the screen. Hit enter. Okay, we get a pretty good idea as to what it looks like, but again, I'm going to zoom box because I want to see these locations along the x and the y axis. And if you remember from the previous video, I said that with a polynomial with the highest exponent of 4, we a lot of times get this W shape, and in this case we have one of the u's dip down further than the other one. Sometimes that can be the case, so let's see, I'm going to go to zoom, and I'm going to hit box. I need to move my cursor around to the opposite corners of my box. I want to go just above this point right here because I think that's where my y-intercept is, and I'm going to hit enter, and I definitely want to get this far left point on my x-axis. That's one of my zeros, and I'll extend out past the far right of this curve and go down, and I don't need this dip here. I'm not looking for the minimum, and I'll hit enter. It told me to estimate, so what I'm going to do is simply move my cursor around. You might like to use trace to where the cursor is restricted to moving only along the actual curve. Sometimes that can give you pretty good values. Other times, as in this one, it sort of jumps the x-axis, and I think I can get a better picture or a better estimate of my zeros if I just simply move my cursor. Okay, looks like I'm right on top of that x-intercept, and below at the bottom of the graph I can read out the coordinates. So I am going to write x equals negative 2.05. Now I'm going to arrow over to my next intercept, and it looks like it falls around negative 0.4. If you want to write these in ordered pair format, just simply remember that the x-axis is located at y equals 0. Okay, I'm now on my third x-intercept. I have x equal 2.4. And now I'm going to arrow over to my last one. I only have 4 because my exponent of my expression, the highest exponent, is 4. So I have at most 4 zeros. That's a little secret that we'll talk about in a later section, but it's kind of convenient to know now. So I'll just simply write down this last x coordinate, 4.9. I could round it and call it a 5.0, but 4.9 is good enough. And now, since this is a function, I'm only going to have one y-intercept. So I'll go back to my calculator, and now I'll go up along my y-axis and do the best that I can. Okay, you see that we get y equals 12.4. Now we can actually do a bit better than that, and this really isn't estimating, but it doesn't take a lot of time to do this. We can use trace. Once you hit trace, again, to find the y-intercept, we set x equal to 0. So when you're in the trace function, just simply type in 0, and at the bottom of your screen, x equals 0 will pop up. Hit enter, and you get a very accurate value for your y-intercept. In this case, we have y equals 10. So it doesn't take a lot more time to get an accurate number for y-intercept. X-intercepts are a bit more tricky, so I'll just use the cursor to approximate those. Okay, so we're done with our calculator, and now we're about to move on and talk about another characteristic of functions, local maxima and minima. Okay, so just looking at this function here, f of x, real easy to point out maximum and minimums. Okay, now by local, we're saying that it's not the absolute maximum or minimum, but for instance, if you were to stand on the top of any one of these points that I just circled, and you look to the left and you look to the right, then you would see that the curve is decreasing on both sides. Okay, and that means that all of these points are what we refer to as local maximums. And so with that being said, you can probably pick out the minimums. And in this case we have 3 here, here, and here. And again, these are local minimums. And one point may have surprised you, this one. This is not a local minimum. That's because if we stood on this particular point and looked to the right, then it doesn't increase. If you look at these other minimums, no matter which direction you look, left or right, then the function is increasing on both sides. So we just hit a trough in the function. But this one, if you look to the right, it's just simply flat. It doesn't decrease or increase. So this is not a local minimum. Okay. To locate these features of a function, we just simply list their x coordinates. If we start with the local maximum, This particular one looks like it falls at x equal -1. Here's another maximum. This one is located here. It looks like x equals 2. Alright, this sharp one, I am going to say falls at 6, 7. X equals 7. And the last one, if I draw a vertical line straight up and down, starting from 10, 11, 12, 13, x equals 13. Okay, that covers all 4 of my local maximums. Now I only have 3 minimums. Okay, if I read the first one, this looks like it falls right in between 0 and 1, so I'm going to call it 0.5. Here is the second minimum, and to me it looks like it falls on x equals 5. And the last one, I'll draw me a vertical line, dashed line to guide my eye, and this one looks like it falls between 9 and 10, and so I'll say x equals 9.5. Alright, so this time they want us to graph it on our own. They don't actually give us the picture, and so we have to pull up our graphing calculator. Okay, I have something graphed already. I'll go to my Y editor and simply clear it, and I will type in the expression on the right for my g of x. Okay, I have x squared minus 2x plus 2. Okay, and as you probably already know, my highest exponent is a 2. This is a polynomial, and so I'm going to get a parabola that looks something like that. It's a U-shaped function, so we kind of already know what to expect. I'll go over here and I'll simply graph it, and there you can see the bottom of the parabola. Okay, I got lucky, and my graph was already pretty decent. At this point, I want the local minimum. Okay, and as you can see from this little simple picture I drew here, once this function starts to go upward on the right and to the left, it never comes back down. It continues out to infinity for the range, and so I only have a local minimum. For maximum, I'll just simply write D and E for does not exist. Now for my minimum, if I want an accurate value for this location, I can use my minimum, or in other words, my calculate function of my graph. I hit second, trace, brings up my calculate menu. I select minimum. Make sure you don't select maximum if you're looking for a minimum, and I go to the left of the point that I'm interested in, and then I go to the right and I hit enter. I have to hit enter a third time, and now it reads out my coordinates. For x, I have 1.00000 and then a 1,3. Okay. Sometimes these functions can return sort of approximate or slightly inaccurate coordinates. I'm just simply going to use x equals 1 for the location of my minimum. And more than likely, this is the exact location of the minimum. X equals 1. Okay. So, I'm going to move my calculator over so I can find the minimum and maximum of this next function h. Notice again that I've got a 4th degree polynomial, so it's more than likely going to look like a w. It's always good to have some idea or some picture in your mind as to what you expect for a particular function. That may not always be the case. So I have a 2 squared, or a 2x to the 4th power minus 17 x to the 3rd power plus 19 x squared plus 80 x minus 84. Enter. Graph. Okay, and so we can't see the tips of these curves for the W, but we pretty much see all of the edges. I am simply going to zoom out okay, and now I can't see the far left minimum, so I'm just going to use this picture to calculate. Well, no, sorry, I changed my mind. I'm going to zoom out one more time, and then I can always zoom back in or use zoom box to get a better picture. Okay, more than likely I can sort of guess as to the upper and lower limits of my box. I want to make sure I get this inner curve that gives me my maximum. So I'm going to go pretty good ways up along the y-axis and hit enter. Drag my box out to the far right and make sure I go down far enough to get my minimums. And there we go. We see that we have let me draw a better curve. Draw it to the right one. I have 2 local minimums, and then here I have 1 local maximum. Okay, so at this point I simply want to use my calculate menu or function to find these coordinates. Alright, I am going to erase these curves, arrows that I drew. I'll start with my minimums, and I'll move my cursor over to the left minimum, enter. Now I just want to go to the right. I don't want to get more than 1 local minimum or maximum in between the 2 points that I pick. I only want to have 1. And now I hit enter for the 3rd time and it gives me my coordinates. I'm just simply going to list the x coordinate, -0.89. Okay, now I'll find my second one. Enter a third time. Gives me my coordinates, and I have an x equals 5.04 if I round to the nearest hundredth. And finally, I will find my maximum, or local max, more specifically. Enter, right bound, enter, and enter for a third time to read the coordinates. X equals 2.22. Okay, so in this case, for your minimums, probably the hardest part would be zooming around and finding the best picture. The calculator does the rest of the work for you. Okay, so here we start talking about yet another characteristic of a function that we can talk about: increasing, decreasing, or constant. Okay, and we have to orient ourselves from thinking in terms of left to right. What is the y value doing as we move along the function from left to right? Well, obviously, in the case of this first curve, we are increasing. Okay, if I were to walk along this curve, with each step I would reach a higher and higher point on the y-axis. Okay, with this particular one, if I were to travel from left to right, I would always, with each step to the right, go downhill. Each successive step would be lower with respect to the y-axis, the vertical axis. So we say that this curve is decreasing along the entire x-axis from negative infinity to positive infinity. And last but not least, we see this flat curve here. Okay, it never goes up, it never goes down, so we refer to this as a constant interval from negative infinity to positive infinity. Now, all of these behaved the same way across the entire x-axis, but that doesn't necessarily have to be the case. Okay, if we try to think of it in more mathematical terms, okay, we're given this little bit about x2, x1, f of x2, and so on. Okay, this is more or less saying that if I pick an x2, and again, that just means a point that's farther to the right. Okay, so for instance, for this function in the middle, let's say I pick x equals negative 1/2 for x1. Then for x2, I definitely want to pick a value for x that's bigger or to the right. So let's say I pick x2 equals 2. Okay, and we're just simply obeying this this inequality here. 2 is greater than negative 1/2. If we do that, and this particular function is decreasing. Then we get f of x2, which would simply be this value, f of x2, whatever y coordinate we get for this point on the function, it is going to be less. It is going to be lower with respect to the y-axis than if we traced x1 back to the function and we came up with a value for f of x1. And let's say that we get about 3.5. So according to my points that I picked, f of x1 is 3.5, and for f of x2, let's say I get a -1, and that turns out to be the case. So my function is decreasing. That's what all of this function notation and these inequalities mean. Okay, now we see some examples of functions that have several different types of behavior. A, okay, from left to right, we can see that we are increasing. Once we hit the middle, we see that we are constant. And then once we get to the far right, we're going downhill. We are decreasing. So this one exhibits all three types of behaviors. And down below, we just simply want to write out the intervals and interval notation. For increasing, we would say it increases from -infinity, the far left, up until we get to -1, and we would put a bracket on -1. Now in the middle, we would represent that interval as from -1 to +1. This is our constant. Oh, I put that in the wrong spot. I'll go back and move it. Okay, that was my constant. So I want to put that on the last line. Bracket -1 to +1. And then finally, this last interval, I'll pick it back up where the constant interval left, +1, which is right here. And we go downhill, we decrease all the way out to +infinity. So once you find your start and stop points for these different behaviors, it's pretty easy to pick out the intervals. Okay, this first one, we are decreasing. The middle one, again, it's flat, we are constant, and then in the end we are increasing. And remember, you need to orient yourself as going from the left to the right. So for increasing, we start at 1. Oh, and I just noticed, no, I got that right. Okay, increasing, we now go from 1 to infinity. So our interval notation sort of swapped. Decreasing was our first interval, which starts at -infinity up until -1, and then again constant in the middle. So we'd say bracket -1, bracket 1. Pretty much the only time we use a parentheses for a specific number is if the function comes to an end or we have an open dot. So I'm simply going to label this graph as to its behavior, and you see that we're either always going up or we flatten out. There is no downhill region of this function. So for decreasing, we would say DNE does not exist. Okay, constant was the middle again, so bracket -1, bracket 1. And then increasing, we've got two intervals, negative infinity to -1 bracket. And now we would use the union symbol and pick it back up for this far right interval from 1 to infinity. And also we always use parentheses with infinity symbols. Okay, the last two for increasing, decreasing, at least on this page. For this one, we now see that we have no increasing interval. We go from decreasing to constant back to decreasing. So for increasing, we would write D and E for does not exist. We would start our decreasing interval at negative infinity. Decreasing interval would be broken up into two intervals joined together with a union symbol. And then the far right interval from 1 to infinity. And finally our constant interval again from -1 to 1 with brackets for each. Okay, and so as you're starting to see, we sort of use, well in this case we can't say that we use our local minimum and maximum because neither one of these points are local minimum or maximum. But in this case, you can see that we have two turning points here and there. We have a maximum and we have a minimum. And that sort of breaks our function up into three parts, like the previous examples that we worked. So now we want to find our new values. And I am simply going to call this one -2. And this other one I will call 2.2. Okay. I could probably get a more accurate value for those, but just to make things simple, this first maximum is -2 and the second, or the minimum, is 2.2. These are going to be my boundaries of my increasing, decreasing, or constant intervals. Now, as far as constant goes, we don't see any flat areas of this curve, so constant does not exist. Now on the far left we have increasing, and again on the far right we have increasing, and now in the middle we have decreasing. We are going downhill. So let me just fill out these intervals at the bottom. Increasing from negative infinity up to my first turning point, -2. Let me put a bracket with that. Union. And then I'll pick it back up with 2.2. I don't want to include this center portion. The far right is where my function is increasing, so it starts at 2.2 out to positive infinity. And now for decreasing, just the center portion from -2 to 2.2, brackets for each. Okay, so now we're given some functions that we've already seen before. Well, actually I think we were given a 3x minus 1, but anyway, what we're going to do in this case is take our calculator and graph these functions. Okay. Um, the first one may not be necessary. Hopefully you recognize that as a linear function, but we'll graph it anyway. Okay. And so we graphed negative 3x plus 1. And you can see that from left to right, we are going down. We are decreasing. And it's a straight line. This is a linear function. So this one exhibits the same behavior throughout the entire x-axis. So for increasing, we would write d and e. For decreasing, we would say from negative infinity to positive infinity. And then again, we had a slope. There was a slant to it, and it was a straight line. And so d and e for constant. There were no flat portions of the function. Okay. So I'll bring my calculator back, and we'll plot this parabola. Okay. Again, notice that the highest exponent is 2. And if you look at this entire term, it's positive. And so in that case, it may be shifted off of the origin, but it will open upward. It will be U-shaped because I have a positive leading term, and it's going to be a parabola because my largest exponent is 2. So what we need to find is our local minimum so that we can write accurate intervals for these different behaviors. So going back to my y editor, I will put in x squared minus minus 2x plus 2, enter, graph. There's our minimum. I will quickly go to calculate, select minimum, arrow to the left of my minimum, enter, arrow to the right of the minimum, enter, enter for a third time, and again, sometimes this minimum function can approximate or not give you an entirely accurate number. I'm simply going to call this x equals 1. X equals 1. Okay. And if you look at it, at the far left, from left to right, we are decreasing. And once we pass through the minimum and we go on to the right side of the function, we are increasing. There are no flat portions of this function. So we will say d and e for the constant interval. Does not exist. For decreasing, we start from the far left, negative infinity. We go to our minimum, and we'll put a bracket. And then for increasing, that region starts at the minimum, x equal 1. And again, to locate these behaviors, we use the x coordinates. Past 1 out to infinity for increasing. Okay. Simply clear that because I'm going to have to bring my calculator back up for this last function h. A bit more complicated. We have a 2x to the 4th. Again, its highest exponent is 4, so we're going to have a double U-shaped function. Okay. At this point, you could sort of move around using your zoom menu and find a better picture of the function. This is actually one we did in a previous example. I'm just going to sort of sketch it here. And so we have already found these values for minimums and local max. Okay, so local minimums, I'll list here. We came up with x equals negative 0.89 and x equals 5.03, or maybe 4.04. And then we came up with the max of x equal 2.22. Okay, so with the general W shape, we start with decreasing, then we carry on with increasing, we switch back to decreasing past our maximum, and then past the final minimum we switch back to increasing behavior. There are no flat portions, so for constant we can say D and E. And now we just simply begin writing out our interval notations for increasing and decreasing. Our first one from left to right is decreasing, so I'll pick this one up with negative infinity over to our first minimum, which is negative 0.89, bracket, union. And then we skip this second portion that increases and pick it back up with the local max at 2.22, and from the max to the last minimum it decreases, and so our last minimum is the 5.04. I'll close that with a bracket. And so we've included all the intervals, just the first and then the third portion here. Okay, now for the increasing. The increasing picks up after the first minimum right here, and that is at negative 0.89. Continues to the maximum at 2.22. Union symbol to sort of mathematically join these two intervals. Union just simply means this interval or the next. And we pick up the final portion of the increasing interval with the 5.04, and it continues that behavior out to positive infinity. Okay, even functions and odd functions. When we refer to even and odd, we're simply talking about the symmetry of the function. Even, if you can mirror it about the y-axis, then it's even. Okay, just simply fold it along the y-axis, fold it over, and if the two pieces match, then it's even. Okay, for odd, we can say that you cut along the y-axis and simply rotate it 180 degrees around to where the two halves are overlapping, and if those curves match, then we say it's an odd function. I was hoping I could fold them over, but you'll just sort of have to picture it in your mind. If we were to cut this piece, or in this case fold it along the y-axis and fold it over to where the two halves were overlapping, okay, you would see that the curves match. Okay, a more mathematical way of saying that is if, for instance, let's say I pick an x value on the left, x equals negative 7.5. If I go to the opposite x value, a plus 7.5, then mathematically I am going to get the same f of x. So if I calculate f of negative 7.5 and then I calculate f of positive 7.5, if this is even, I will get the same number. And if you'll look, we just start with these 2 points and we draw a horizontal line over to the y-axis. You see that they are on the same level. Now that has to be true for all the other points along the curve. Okay, but mathematically this is what even means. For a given x, if we take the opposite and we calculate the outputs for each, then those outputs will be the same number. Okay, with this next curve, I think I can actually show you, or in other words, actually cut out 1/2 and rotate it and show you that the two curves match, and it's going to be symmetric with respect to the origin. Okay, so if I take this curve and I simply cut 1/2 off, and now if I take that half and I rotate it 180 degrees, you can see that what started out as the left portion completely matches up with the right portion. Okay, I rotated it around the origin, and so it's symmetric about the origin. It's an odd function. Okay, as for the rest of them, we either have to graph them or we have to be clever. We actually have the algebraic expression for f, d, or I'm sorry, g, h, and l. Okay, x squared. One of our basic functions, it's simply a parabola that more or less looks like this. Okay, maybe a little bit more symmetric. I can bring up my calculator and show you a better picture. Okay, so in other words, if we took this function, this curve, and cut it along this y-axis and folded it, or perhaps not cut, just fold, then the two halves would match. And it turns out that that's the case even if we were to shift it up or down. So for instance, say we had x squared plus 2 and we shifted it off of the origin. Still, okay, it's not on the origin, but if we folded it along the y-axis over onto its right side, then those two halves would overlap. So if we have x squared, okay, plus any constant number, then we're pretty much dealing with an even function. Now, d, which our function's labeled g, we have x to the third. And more than likely by now you've probably started noticing that we have even exponents, odd leading exponent, odd again for h, and then an even for L. Okay, so more than likely G is odd, if anything. We go to our calculator and we clear it. Enter in x to the third. And for an odd function, I can take this one and actually cut the left half with respect to y, rotate it 180 degrees, and the two halves will match. So here's our x to the third. I am going to cut again the left half, move it off to the side, rotate it 180 degrees, and you can see that the two halves are identical. This is an odd function. Now, what if, like the x squared function, I add a constant number to the end? For instance, x to the third plus 2. It's going to shift it off of the origin, up 2 units. See? So I will take this picture, this plot, cut the first half off, the negative half, rotate it 180 degrees, and now you can see that this portion, the minimum, is actually below the x-axis, with the right portion of x to the third plus 2 above. So the two halves don't match. This is not an odd function. Okay, our last two, H and L. You see that H has a degree of 5. It's either odd or it's neither. Okay, so I'll cut this one out. Make it a little bigger. Cut the negative half off and rotate it 180 degrees, and then we'll compare the two halves. And so it looks like they pretty much agree. I would say that this function is odd. Now, notice what happens if I take this previous function we were given h, and if you'll look, I took the 2x term and I changed it to a 2x squared. I've now introduced an even exponent term into the expression. Look at what happened to our graph. It's now no longer symmetric with respect to the origin. As a general rule of thumb, if you look at a function that has the highest exponent as being an odd number and all of the other exponents are also odd, then it will be an odd function. However, if you insert a term with an even exponent, then it will no longer be odd. It would be neither. And that same rule applies to polynomials that have even exponents. As in the case of L, we have exponents of 4, 2, and 0. Let's graph it and take a look at what it shows us. X to the fourth minus 2x squared minus 4. Enter. Graph. Okay, this one pretty much looks like if we were to fold it along the y-axis, the two halves would overlap. Okay, so let's take a look at the function if I were to introduce an odd exponent term without exceeding the highest exponent 4. Let's say, for instance, I take the expression and I insert a plus x to the third power now you can see that our function is no longer symmetric with the y-axis. This is not even, whereas the original L was even. So if we were to go back through our functions, we would say even for A, odd for B, even for x squared, odd for G, odd for H, and even for L. If the expression contains all odd exponents, then the function's odd. If the expression contains all even exponents, then the function is even. Okay, so here's our last example of section 1.2. We want to maximize the volume of this shape. Let's see. And they want us to use the graphical techniques to estimate the value of x, or the maximum volume. So we'll start with our basic equation or formula for volume. Volume equals length times width times height. I will call this expression the length, h the height, and 7 minus 2x the width. I simply insert those expressions into my function, or my formula. Width is 7 minus 2x, and h is x. Now we're going to use our calculator for this, so it's not entirely necessary to actually distribute these different factors together. I'll just simply pull up my calculator. And type in my factors, x plus 2. 7 minus 2x, and then finally x. Doesn't really matter what order you put them in, as long as you get all of the factors into the y editor. And now we're going to graph. Okay. So we're looking at volume, okay, and once again we're dealing with real world quantities. These are dimensions. Volume is a real world quantity. Basically, how much space does something contain? So we want our volume to be positive or 0, and we also want all of our dimensions to also be positive or 0. Okay, these are real world values that we would come up with. We would never say that we came up with a negative quantity for either of these. Okay, by saying v is positive, with our calculator we're using the variables y and x. So as far as my calculator goes, I'm saying that y is positive or 0, and x is also positive or 0. Okay. And if you'll remember, in terms of our coordinate plane, quadrant 1 is the only space where both of these are true. Okay, x, this is the positive direction for x, and the positive direction for y. We're not interested in what the rest of the curve does. So going back to my calculator, here is our function for our volume. I will go to zoom, and I'll restrict myself to quadrant 1. Okay, we didn't get the entire curve, but you can obviously see that the curve comes up, peaks, and then drops back down. So I'll have to zoom out, or I could use my window. Let's see if I can put a Y max so that I can see the top of my curve. Okay, 15 wasn't enough. I'll go back to my window and I'll say 30. Graph, and there it is. Okay, this is our volume function. Initially, as x increases from 0, our volume increases. Then we max out at some particular value of x. We want to know what that value is. This is our local max. Past that value of x, our volume decreases. We want to maximize the volume of our box. Again, the calculator is going to do the work for us. We just simply go to second, calculate, maximum. I want to arrow over to the left of my maximum, hit enter, pick the right bound, make sure I go sufficiently past my max, hit enter, enter a third time, and we read our values for x. Remember, our length, width, and height depend on x, and our volume is essentially our y value. So what this tells us at our max is that we get a maximum volume of 24. We weren't given units, so we can't assign units to our volume. We could just simply say 24 units cubed. And to answer the question read, estimate the value of x for which the volume of the following rectangular box is maximum. There we go. In our workbook, we could simply write x equals 2.1 and maximum volume, V sub max, would be 24.1.